So let us start with some doubts. If you have any doubts, you can ask. So in this session, we are going to cover number systems, then Boolean algebra, then we are going to cover logic gates. So myself, Sunil Manjani, having 16 years of experience as gate tutor. So we are going to cover these three topics. Okay. So first of all, what is number system? Okay, numbers, as you know, are divided into various categories. Numbers. So basically, we are dealing with decimal numbers. Decimal numbers. Okay. Decimal numbers. These are one decimal numbers. We are also dealing with binary numbers. And then hexadecimal numbers. Hexadecimal numbers. Okay. Hexadecimal numbers. Okay. So first of all, we'll deal with decimal numbers. Sorry. Decimal numbers. Decimal has a term DEC. That means, so it is derived from the word decim. Okay. It is a Latin word. It means 10. It means 10. So if you count the numbers from 0, 0, 1, 2, 3, 4, 5, 6, and 7, 8, 9. So these are all 10 numbers. Okay. So these numbers will have their place value also. So this is place value is units, tens, hundreds, thousand, 10,000, and 1 lakh. Okay. So when we are covering with, suppose some number, suppose some number, okay. So tens are units. Suppose I am saying number 746. So this rightmost number has units place. Second to the right towards its left is has tens place. Then the first number here has hundreds place. Okay. So if I say, if I want to represent this number, suppose I got a number that is 2945. 2945. Okay. This is not same as 2495. Remember this. Okay. So I can represent 2945 like this. So this is units place, this is hundreds place, this is sorry tens place, this is hundreds place, this is thousands place. Okay. So when I say unit in decimal, the base or the radix is 10. So 10 raised to 1. When I say tens, sorry, 10 raised to 0, first of all. When I say tens, 10 raised to 1. When I say hundreds, it is 10 raised to 2. When I say thousand, what it is? 10 raised to 3. Okay. So 2 is in thousands place. So I will represent this as 2 into 10 raised to 3. Plus, I will say 9 into 10 raised to 2. Plus 4 into 10 raised to 1. Plus 5 into 10 raised to 0. So this is 2000 plus 900 plus 40 plus 5. Okay. So you can perform simple addition here as you can see 2000 plus 900 is 2900, 940 is 2940 plus 5. So you get 2945. 2945. So this is decimal number system. Okay. You can represent any number with decimal number system. Okay. Any number with decimal number system. So let us see. Binary number system. Okay. So binary number system. Okay. So it has again came from the word Latin word that is binarious. That means 2. What is its characteristics? It is represented by 2 symbols, 0 and 1. 0 and 1. Okay. It is also positional. Okay. 1010 is not equal to 1100. Okay. Remember that. Whenever I want to represent a binary number, okay, I will say 1010 B. I will write down suffix B. Okay. Suffix B. Okay. So here if I want to represent binary with 0 and 1 only, 0 and 1 only. Okay. I will say this is nothing but bits. Bits. Bit 0, bit 1. Bit 0 and bit 1. Okay. Bit 0 and bit 1. Okay. Bit 0 and bit 1. Okay. So now I want to represent bytes. I want to represent bytes. Okay. So if I want to say 4-bit number. Okay. So how it will be? 0101 000, sorry, 0011. Okay. So this is actually a 2-bit number. Okay. It is a 2-bit number. Okay. So similarly, you can represent 8-bit number. Okay. So 8-bit number means 1 byte. Okay. 16-bit number, 2 bytes. 1024-bit number, 1 kilobyte. 1024 kilobyte is 1 megabyte. 1024 megabyte is 1 gigabyte. 1024 gigabyte is 1 terabyte. Okay. You can ask questions on this topic also. I will explain. Okay. So let us see. I'm not able to see chats. Let us see where I can. Yes, let us see. Just a minute. Just a minute. So we'll convert binary to decimal. First of all, decimal conversion. Okay. Okay. So we'll convert this. Okay. So this binary to decimal. Okay. So decimal is 0. So equivalency will show decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So binary, what you will get is 0, 1, 0 and 1. For 2 place binary, this is 1, 0. This is 1, 1 for 3. Okay. For 4, 1, 0, 0. For 5, 1, 0, 1. For 6, 1, 1, 0. And for 7, 1, 1, 1. For 8, 1000. For 9, 1001. For 10, 1, 0, 1, 1. Sorry, 1, 0, 1, 0. For 11, you will get 1, 1, 0, 1. For 12, we'll get 1, 1, 0, 0. This will be not, this will be 1, 0, 1, 1. This is 1, 1, 0, 0. For 13, you will get 1, 1, 0, 1. And for 14, you will get 1, 1, 1, 0. And for 15, you will get 1, 1, 1, 1. Okay. So in all 16 decimal numbers, you will get this binary. Okay. So you can say that you can convert decimal into binary. Okay. So how it is done? Decimal into binary. We will see example. Oh, sorry, binary into decimal. So we want to convert 100,101 binary to decimal. Okay. Binary to decimal. So how you will convert? So this is units place, tens place, hundreds place, thousands place, and this is what? 10,000 and 1 lakh. Okay. So first of all, we'll see units place. So rightmost side, we'll write down 1 into 10 to the power 0 plus this is 0 into 10 to the power 1 plus 1 into 10 to the power 2. Okay. 1 into 10 to the power 2 plus 0 into 10 to the power 3 plus again 0 into 10 to the power 3 plus 1 in, sorry, 10 to the power 4. This is 1 into 10 to the power 5. So these are your 1 0 0 1 0 1. Okay. So we have put the weights on radix or base 10. Okay. So you can convert this one. Okay. So this is one of the way. Other way you can find out. Okay. Next we will see decimal to binary conversion. Decimal to binary conversion. Okay. So suppose number is 37. So we'll write down number is 37. Okay. So we know that maximum power is 2 raised to 5. So I will write down question mark into 2 raised to 5 plus question mark into 2 raised to 4 plus question mark into 2 raised to 3 plus question mark into 2 raised to 2 plus question mark into 2 raised to 1 plus this question mark into 2 raised to 0. Okay. Then we'll see, we'll fill in the templates. Okay. Okay. So how to convert this? Okay. So we got 37. When we divide it by 2, what we'll get is 32 will get answer. Okay. Okay. 32 will get answer and sorry, 36 will get answer for 18. 18 to the 36 and remainder is 1. Okay. Like this we'll see 37 by 2 is equals to 18 answer question and remainder. Remainder is 1. Then question is 18. Divide 18 by 2. This is 9. Remainder is 0. Then divide 9 by 2. This is 4. Remainder is 1. 4 by 2. This is 2. Remainder is 0. 2 by 2. This is 1. Remainder is 0. Okay. 1 by 2. Remainder is 0. Oh, sorry. Question is 0. Remainder is 1. Okay. So this is your remainder and this is your binary equivalent. 137 decimal is equal to 100 sorry, this is equal to 101001 binary. So in this way you can find out decimal to binary equivalent. Okay, decimal to binary equivalent. Okay, So this is how to convert decimal to binary. Okay. So let us see. Let us see next example. Example is 43 decimal. You have to convert it into binary. So 43 divided by 2, you will get quotient and remainder. 43 divided by 2, you will get 21. Remainder is 1. 21 divided by 2, you will get 10. Remainder is 1. 10 divided by 2, you will get 2. Okay. This is 5. 2 divided by 2. Oh, sorry. This is 5 and remainder is 1. So 5 divided by 2. This is 2. Remainder is 1. 2 divided by 2. Answer is 1. Remainder is 0. 1 divided by 2. Answer is 0. Remainder is 1. So 43 decimal is equal to 111101 binary. In this way, you can convert the binary. Okay. Convert into binary. Okay. So let us see third number system, that is hexadecimal number system. Hexadecimal number system. Hexa means 6. Decimal means 10. So you got 16 symbols. Total 10 plus 6 is 16. Okay. So it will be like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10 symbols. Then letters A, B, C, D, E, F. 6 letters. Okay. It is also positional. That means A1 3D hexadecimal is not equal to 3D A1 hexadecimal. Okay. Okay. So it is mainly used by computer programmers. Mainly used by computer programmers. Okay. So we'll see conversion binary to hexadecimal, conversion okay. So you know that 16 is 2 into 2 into 2 into 2. So I'll say 16 raised to 1 is equals to 2 raised to 4. So I will say one hexadecimal digit corresponds to 4 binary digits. 4 binary digits. Okay. So what I will do is we'll write binary and its equivalent hexadecimal. In next slide we'll do that. So binary equivalent hexadecimal. Okay. Binary 0 1 0 1 0 1. We'll write down decimal also in place of decimal. Okay. 0 1 2 3 4 5 6 7 8 9 10 11 12. Okay, in place of, just a minute, in place of 11 12, we'll write down A B C D. Okay, A B C D E F. This is hexadecimal. Okay, let us say this is hexadecimal. Okay, this is binary. So 0 1 0 1 0 1 0 1 0 1 0 1. This is 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1. Okay, so this is 1 1, sorry, 0 0 0 1 1 1 0 0 0 1 1 1 0 0. Sorry, this will be and then one. Okay, this is 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1, like this. Okay, so you can convert this by using this table. Okay, hexadecimal to binary or binary to hexadecimal, you can convert. Okay, now we'll see decimal to binary. Decimal to binary. Bhargavi is asking how to convert base 4 into base 16. I will tell you after this conversion. Okay. Base 4 to base 16. I will tell you. Just let me complete this. Decimal to hexadecimal. To hexadecimal. Okay. So we have got 25 hexadecimal. We have to convert this into decimal. It is hexadecimal. So we will convert this into 5 into units place 16 raised to 0 plus 5 into tens place 16 raised to 1. So 5 into 16 plus 5. So this is 80. Oh, sorry. This will be 2. No? Yeah, this is 2. Okay. So 2 into 16, that is 32 plus 5. That is 37. Okay. So decimal into hexa, this one. Okay. You can convert decimal, hexadecimal into decimal. This will be hexa to decimal. You can convert decimal to hexa by doing this. Suppose you got decimal 37. So 37 divided by 16 will give you quotient and remainder. Quotient is 37 divided by 2. Okay. Divided by 16. So 37 divided by 16. So 16 into 2 is 32. Okay. So 16 quotient is 2. Answer will be 32 and remainder will be 5. 37 minus 32 is 5. Okay. 2 by 16, naturally quotient will be 0, remainder will be 2. Okay. So if you go from bottom to top, you will get 25 hexadecimal. In this way, you can convert 25 hexadecimal to decimal and decimal 37 into hexadecimal. Okay. So simple technique. Okay. So now we'll come to some query. Bhargavi was asking how to convert base 4 into base 16. Just a minute. Okay, so you want to convert base 4 to base 16. Base 16. Okay, so suppose x equal to 4 and y equal to 16. So you can convert base x to base y. Base y. Okay, for that what you need to do is step 1. Step 1, convert base x into decimal. Decimal, that is base 10. Okay, then convert in step 2, convert base 10 into base y. Base. Okay, so suppose I want to convert 372.34 base 4 to base 16. Base 16, how I will convert? Okay, so I will do like this. 372.34 base 4 is equal to 3 into, this is units, tens, hundreds. 100 means 10 raised to 2 plus 7 into 10 raised to 1 plus 2 into 10 raised to 0. 0.3 into 10 raised to minus 1 plus 4 into 10 raised to minus 1. So this will be what? 300 plus 70 plus 2 0.3 plus 0.4. So this will be what? I'm sorry. Just we'll see this number. I'm sorry. Okay. To convert 4 into 16. So let us see. 3 into this one to convert into base 4. Na? Base 4, 4 into 2. This is hundreds place. Plus 7 into 4 raised to 1. Plus 2 into 4 raised to 0. 3 into 16 plus, this is 28 plus 2. What is 3 into 16? 48 plus 28 plus 2. So this is 78 decimal. Okay. Now you can convert this 78 decimal into hexadecimal. How to convert? 78 divided by 16. Divide by 16. So question and remainder we'll see. Okay. So this is 16, 3 of 48. 48 plus 32 will give you 80. So 16. 4, yeah. Okay. 16 4 is 64. So this is 64. Question is 464. This is 4 and this is 1. Okay. Here 64, remainder is 14. Now you will divide 14 by 16. Question is 0. Remainder is again 14. Remainder is again 14. Okay. Then you have to convert this into, what do you mean by 14? See here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. This is 15. So you'll get this one as E, this one also as E. So this will be equal to EE16. EE16. Okay. So in this way you get from 372 base to the base 4, you'll get EE16. Okay. So this is your conversion. This is your conversion. Hope Ayushi can, Bhargavi has understood this. Okay. So basically you have to follow two steps. Convert base x into decimal, then convert base 10 into base y. Okay. So this is explanation. Okay. Any other doubt you can post it on, I'll solve. Any number conversion, it is applicable. Okay, you can solve it by any number conversion. Any number, okay. You can convert it to, convert it with any base x to base y. You can do any conversion. So next is we'll see octal number system. Okay, octo means 8. So 8 numbers in decimal are 1, 2, 3, 0, 1, 2, 3, 4, 5, 6 and 7. Okay. So it is also positional 1743. Octal means 0 is not equal to 73140 octal. Or you can write down 17438 is not equal to 73148. Okay. So how to convert decimal to octal? Conversion. Decimal to octal. First of all, we'll see. Decimal to octal conversion. Okay. So decimal to octal conversion is, we'll convert 37 octal to decimal. Okay. So this is units place. This is tens place. So first of all, we write down 7 into 8 raised to 0 units place plus 3 into 8 raised to 1. So this is 24 plus 7, that is equal to 31. So 37 octal is 31 decimal. Sorry, this was octal to decimal. I'm sorry, octal to decimal. Now decimal to octal. Remember that you are converting octal to decimal. So octal is the base you are given, but number you're not given is of base 10. So we'll use always base 8, whatever base is given. Okay. So decimal to octal. Suppose we want to convert 37 decimal to octal. So base given is 10. Okay. Unknown base is for base 8. Okay. So in this case, what we'll do is whenever we are multiplying, we will use the given base. Whenever we are dividing, we'll use the unknown base. Remember, multiplying, you will get known base, use known base, and while dividing, use unknown base. Unknown base. Here, known base is this, unknown base is this. So we want to divide 31 by 8. That is question and remainder. Question is 31 by 8. 8 3 ja 24. 24, 31 minus 24 is 7. 3 by 8. Question is 0. Remainder is 3. So from bottom to top, this will be 37 octal. 37 octal digit number. Okay. So this is octal to decimal and decimal to octal. Now we'll see binary to octal. Binary means, okay, decimal to binary to octal. Octal is 8. We have to find out equivalent binary. So 8 is equal to 2 into 2 into 2. So 8 raised to 1 is 2 raised to 3. So one octal digit gives 3 binary digit. Okay, 3 binary digit. So first of all, we'll see binary to octal. Octal. Okay. So numbers are, if you want to see the conversion table, binary, equivalent, octal. We'll say decimal and then we'll say equivalent octal. Decimal we can write down straight away. 4, 5, 6, 7, 8, 9. This is 0, 1, 0, 0. Sorry, 0, 1, 0, 1. Just a minute. 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. Okay. Then we can write down 0, 0, 0, 1, 1, 1, 0, 0, 0, 1. Like this. Okay. So how to write down equivalent octal? 0, 1, 2, 3, 4, 5, 6, 7. That's it. Okay. After that, you got 8. Then you can write down 10. Then 2-digit number. First 2-digit number. 2-digit number. Then 11. If you got 10, then you can write down 12. Okay. So like this, you can write down octal and decimal. So you can directly convert binary to octal, octal to binary from this table. Okay. So I will tell you how to write down decimal to octal. 1, 2, 3, 4, 5, 6, 7. Sorry. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is decimal. This is octal. 0, 1, 2, 3, 4, 5, 6, 7. Okay. Then 10, 11, 12, 13, 14, 15, 16. Okay, how many numbers? 1, 2, 3, 4, 5, 6, 7, and then 70. 8 numbers. So this is group of 8 numbers, you can say. This is 8 number, this is 8 numbers. 1 digit, this is 2 digit number. Okay, so this is 1 digit and 2 digit number. So in this way you can write down 1 digit and 2 digit, octal to binary, binary to octal conversion. Okay. So this is number system. Okay. Any doubt you have, you can ask. Okay. So I think no. So we'll move on to Boolean algebra. Today's second topic. Okay. Here, suppose I have got a door. I got a door. Okay. So in Boolean algebra, in normal terms, door can be fully closed, half closed, 3/4 closed, or fully open like this. Okay. Fully closed, fully closed, half open, 3/4 open, and Okay, fully open. Fully open. Okay, so this is door position, but in Boolean terms, this is normal terms. In Boolean terms, this door is either open or closed. So suppose you denote open by 0, then close is denoted by 1. Or if you denote open by 1, close is denoted by 0. Close is denoted by 0. Okay. So any signal which has value greater than 0, this is denoted as 1. Which has value equal to or less than 0, it is denoted as 0. Okay, this 1 is called as high signal, 0 is called as low signal. Okay, 0 is called as low signal. Low signal. Okay, so this is crux of Boolean algebra. So we have got variable. Suppose we have got variable a. Complement of variable, its complement is a bar. It is denoted as bar. Okay, or you can say over bar, a bar over. Okay, so if a equal to 0, then a bar is equals to 0 bar, that is equal to 1. Okay, if a equal to 1, then a bar is equals to 1 bar, that is 0. That is 0. Okay, we got some functions in Boolean algebra. First is ORing. OR means adding. Made be signal, made be waveform. Okay, ORing, or means adding. Okay, so suppose there are three variables a, b, c. You can a or b implies a plus b. A or c implies a plus c. A or b or c implies a plus b plus c. Okay, a plus b plus c. What do you mean by in terms of switching action? Okay, because whenever I am saying that door is closed or door is open, student A is writing down, teacher, there is one of my exercise, but I have no idea. Would you and everyone help me? Student A, changing ABC into system that has only one NOR gate and one NAND gate. Whenever we come across the topic of K-map, okay, your topic is related to K-map. Okay, So be connected with Ekeeda channel. Okay, this one. And whenever we are going to come to this K-map, I will solve your doubt. Okay, changing ABC into system that only have one NOR gate and one AND gate. Both are two inputs. Okay. Do you have any figure with you? Any question? Proper question? You can mail it to Ekeeda. You can mail it to Ekeeda. Address is given. Okay. Okay. A B C dash. Okay, fine. Is it A B C dash? A B and C complement, isn't it? Okay, just I will note it down. Okay. Let me note it down. Okay. Okay. Now we'll move on to other topic. That is how it electrically how it goes. Okay. This Boolean algebra, Boolean expression. Okay. So here I will write down Boolean expression. This is description, circuit. Okay. Boolean algebra law. What is the law or rule? Rule. Okay. We'll see one by one. Okay. So first is variable a plus 1. A plus 1. So this is 1. So you can consider this as 1 as closed. Okay. 1 as closed. So its value is 1. This is some signal, high signal. This is not 0. Non-zero means high. Plus 1 is again high. Okay. Therefore, value is high. That is 1. That is 1. Okay. So you can say that A in parallel with closed. That is equal to closed. That is equal to closed. So see here. This is closed. And this is any position A. Any position A. Okay. Any position A. So this is, and this law is annulment law. Annulment law. So anything plus 1, that is non-zero quantity plus 1 is 1, non-zero quantity plus 0 is 0. Okay, A in parallel with open, with open. Okay, so this is open, this is switch position A. Okay, this law is called as identity law. Identity law. Okay, A multiplied by 1, A dot 1, you cannot write X because it is using K maps. So A dot 1 is A multiplied by 1. So this is A in series with 1, with closed, I will say 1 means closed, that is equal to always A. So A in series with closed is always A. This is also called as identity. This is also called identity. Okay, A dot, or rather A plus A is equal to A. A plus A is equal to A. A in parallel with A. That means this switch A, whatever is the position, this will be in parallel with other switches with same position. That is A. So if both are 0, suppose open means 0, so you'll get 0 answer. If both are closed, you'll get answer 1. So whatever is the position of A, you'll get answer A. This is called as idempotent law. A dot A, that is equal to A. A in series with A. So switch A in series with switch A, whatever is the position. Anyone is open, you will get same switch position. Okay, so this is called as again idempotent. Anyone is open, circuit is open, therefore A. Anyone is closed, anyone is closed, again you will get A. Okay, because one is closed, other will be open, so you will get A only. So another is not A bar. Not A bar means negation. Again, negation of negation is positive, therefore A. Not A is A. Okay, this is known as not A. Double negative. This is equal to A bar or A, simple A. Okay, not A bar. This property is called double negation. It has got no circuit. Okay, A plus A bar is equal to 1. That is A is parallel with not A. Not A means A bar. So how it will look like? A is open switch, not A means closed switch. Okay, so this is open. So what you will get is here, open means 1, so signal will come here, from input to output, signal will come through this A naught, A bar. Okay, so signal will come means it is 1. This is 1. This is the case. You can reverse it also. Okay, if this is closed, this is bottom one is open, this is A bar, again signal will come. again signal will come. Okay, so this is called as complement. Okay, so again we'll see another one, that is a dot a bar, that is equal to 0. A dot a bar, that is equal to 0. Hello sir, please give your contact number. I have supply exam of. We cannot give our contact number. You can always contact Ekeeda. There are many lectures available on digital electronics. Okay, or you can ask them for my contact number, because I have no authority to give you contact number. Okay, Merajuddin, hope you can understand. Okay, you can search for ekeeda.com. Okay, and contact the. Yeah, we can help you, but you have to contact our support. Okay, you can contact our support, Ekeeda support. They will help you definitely. Okay. They can connect you with me, no problem. Okay. So a dot a bar is what? 0. How you can see that? That is a in series with not a. Not a is equal to 0 means open. So this is a in series with not a. Okay. So this is a in series with not a. That means it is open. That means it is open. Okay. So let us see. This is a. This is closed. This is if a open, a is closed. So this is again a complement function. Complement function. Okay, if any switch is open, signal will not get here from input to output. So you will not get any output. So it will be 0. Okay. Another one is a plus b equal to b plus a. So consider these as currents. So a in parallel with b is equal to b in parallel with a. Okay. So parallel circuits. A and B. This is called as commutative. Commutative law. Okay. A dot B is equal to B dot A. A in series with B is same as B in series with A. This is but natural. Okay. But natural. There is no need for any explanation for this. It is from observation only. A in series with B is B in series with A. Commutative law. Okay. Commutative law. A and B. Let us say that I have got A plus B. We have seen what is A plus B? B plus A. So A plus B complement is nothing but A complement B complement. Okay. This is or, plus means or, this means and. Okay. That means or is inverted. This means inversion. Bar means inversion. I will say or is inverted to get and. Remember this. This is De Morgan's theorem. A plus B, sorry, A dot B is equal to A bar plus B bar. That means and is inverted to get or. This is first law, this is second law. Again, it is De Morgan's law or De Morgan's theorem. Okay. So these are basic law of what? Boolean algebra. Okay. So these two are very important. Others are also important, but these two are very important. Let us see postulates. Okay, Boolean postulates. Okay, 0.0 is equals to 0. Okay, 1.1 is equals to 1. 1.0 is equal to 0. Like this, 0 into 0 is 0. 1 into 1 is 1. 1 into 0 is 0. 0 plus 0 is naturally 0. 1 plus 1 is equals to 1. 1 plus 0 is equals to 1. 1 bar is equals to 0. As I have explained you, 0 bar is equals to 1. Okay. Distributive law. Another law is distributive law. These are Boolean postulate, distributive law. Distributive law. We'll see. Okay. So this is first law, that is called as OR law or distributive law. A into B or C is equals to A into B plus A into C. Second law is AND distributive law, that is called as A plus B dot C is equals to A plus B dot A plus C. And distributive law. Okay, remember this. Then we have got absorbative law. Absorbative law. Okay. So first one is A plus A dot B. Whenever I say A, it is A into 1. isn't it? A dot B. So this is equal to A dot 1 plus B. Second is A plus B, that is equal to A means A plus 0, isn't it? A plus 0 is A. Similarly as 1 plus 0 is 1. So dot A plus B. So this is equal to A plus 0 dot B. That is equal to A. Okay. So this is absorptive law. Next one is associative law. Postulates is different. You can say what are the postulates? These are the postulates, Boolean postulates. Okay. These are different, you can say operation and or operation. And or negation. Negation or complements. These are some observations from Boolean, De Morgan's theorem or Boolean laws. These are some observations from Boolean laws. Okay, just observation from Boolean law. These are applicable to binary systems. Okay, binary systems. Okay, so just you remember this table. This table is sufficient. Okay, whatever I told you, remember this table. Okay, and remember these laws, extra laws. That is, this is distributive law, absorptive law. Okay, associative law. Okay, what is associative law? Okay, we'll see associative law. Okay, so this is A plus B plus C is nothing but A plus B plus C. This is same as A plus B plus C. This is first associative law. Second associative law is A into B plus C is equals to A dot B into C. This is same as A dot B dot C. Okay, A dot B dot C. Okay, so we'll see one example on all these laws. Okay, one simple example. One simple example we'll see. Okay, we got example. I'll write down with other color. So let us see one example. We have to simplify this. Simplify this. Okay. How many terms are there in this? There are 4 terms. There are 4 terms. We'll simplify. That means reduce the number of terms. Number of terms will reduce. Okay. So we'll go with the solution. So our question is A plus B dot A plus C. So this I will open up A dot A plus A dot C plus B dot A plus B dot C. This is equal to A dot A plus A dot C. B dot A is equals to A dot B. We have seen this plus B dot C. This is which law? Distributive law. OR gate, then sir, OR gate or AND gate. Okay. Not gate. Yes, you can say that. OR gate, AND gate, and not gate. Okay. This law is used to design gating circuits. Okay, or gate circuits. So question is this one. Okay. So this is first law. You have to simplify this, isn't it? So this is equal to what is A dot A? A dot A is A plus A dot C plus A dot B plus B dot C. This is called as idempotent AND law. That is A dot A is equals to A. Okay. Then we'll see next step. It's the same problem, same solution is going on. Okay, different stages, different laws we are using. Okay. A dot A plus C. Consider this statement. A into 1 plus A dot 1 plus plus A dot B plus B dot C. This is distributive law. Okay. Then we'll see next step. That is equal to 1 plus C is again high because C is greater than 0. Any positive signal. 1 plus greater than 0 means high. 1 plus high is high, that is 1. So A dot 1 plus, this is same, A dot B plus B dot C. This is identity or law. Or law. That is 1 plus C equal to 1. Okay. Then we'll go to next step. That is, this is, consider this A into 1 plus B plus B dot C. This is again distributive law. Okay. Okay. So come to next step. This is equal to 1 plus B is 1. B plus C. Identity or law. Or law. Okay. What is A dot 1? A dot 1 is anything dot 1 or A multiplied by 1 is A plus B dot C. Okay. So I can say that A plus B, A plus C is equal to A plus B dot C. A plus B dot C. So this is the answer for this problem. Okay. Hope you can understand. So you understand this one. Okay, so this completes your Boolean algebra. So last topic for the day, because we are into closing session. Okay, any problem in this, any difficulty, you can ask. Boolean algebra not that difficult, it is very easy. Just you remember addition, subtraction, addition and multiplication. Okay, high into high is high, high plus high is high. Okay, high plus low is high, high into low is low. Okay, so Boolean algebra in 4 sentences. High into high is high into low is low. High plus high is high. Fourth, high plus high is high. Oh, sorry. High plus low, I will say. High plus low is high. You can write down 2 more. High, sorry, this is low into low is low. Sixth, low plus low is okay. What you can denote it by? 0 into 0 is 0, or rather I will say 1 into 1 is 0, because it is representing high. Okay, so this is 1 into 1 is 1, 1 dot 0 is 0, 1 plus 1 is 1, 1 plus 0 is 1, 0 into 0 is 0, 0 plus 0 is 0. So this is crux of which law, or which laws? Boolean algebra laws. Okay. Using all this, we'll see gates now, logic gates. Okay. We'll see logic gate. We'll use only 2 input gates. Okay. So let us see what are the type of gates. First one, gate representing multiplication operation. This gate is called as AND gate. Okay. So how we represent AND gate? Okay. This is represented by a symbol like this. This is AND. This is input 1, input 2, and this is output. Q is the output. Okay. So this is 2 input AND gate. Okay. So what is Boolean expression for this? Boolean expression is the relation between digital input and output. Okay, Q is equals to A dot B. Output is equal to A dot B. Okay, what is truth table? Truth table is nothing but representation of operation for various binary signals. Various binary signals. Okay, so we have got signal A, signal B, and output. So binary inputs are like this. This is output 0 1 0 1. Okay, 0 0 1 1. And operation 0 into 0 is 0. We have seen 0 into 1 is 1. Oh, sorry, 0. 1 into 0 is 0. 1 into 1 is 1. Okay. From this, what we can say that if any signal is high, if any signal is, I will say low. Okay. Output is low. Output is low. Okay. Then we have got OR gate. OR gate. Okay. How to represent this? Signifies addition operation. Addition operation. How to get? So this is two input OR gate. This is a symbol. This is OR. A, input A, input B. This is output Q. Boolean expression is Q equal to A plus B. This is Boolean expression. Truth table. Input A, input B, output Q. 0 0 0 0 1 1 1 0 1. Okay. 1 1. Okay. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. So what I will say is, if any input is high, output is high. Output is high. Output is high. Okay. So this is second gate. Third gate is NOT gate. Third gate is NOT gate. Okay. NOT gate signifies negation. Negation or inversion. Symbol is like this. Small bubble with the triangle symbol. So this is input A, output Q. So simply I will write down. Here you can see the signal A will be conveyed. There is bubble symbol. That means this is negation symbol. So simply I will say that Q is equals to A bar. Q equal to A bar. This is a Boolean expression. Truth table. Output A, input A, output Q. If input is 0, output is 1. If input is 1, output is 0. Okay. Output is 0. So this is third gate. Okay. Fourth one will be NAND gate. NAND gate. Okay. What will be NAND gate? It is a combination of NOT and AND. NOT and AND. So this is the symbol. Just a minute. Symbol is like this. This is NAND gate. Introduce small bubble at the output. Okay. So this is input A, input B, output Q. So this is AND. Okay. And this is NOT. So I will say that AND means A bar B. NOT is like this. This will be your output. This will be your truth table. How it will be there? Okay, truth table. Input and output. 0, 1, 0, 1, 0, 0, 1, 1. 0 into 0 is 0. 0 over bar is 1. 0 over bar is 1. 0 into 1 is 0. 0 over bar is 1. 1 into 0 is 0. 0 over bar is 1. 1 into 1 is 1. 1 over bar is 0. So this is your truth table for NAND gate. Truth table for NAND gate. Okay. Next, fifth one we'll see. This is NOR gate. Fifth one is NOR gate. Fifth one is NOR gate. Okay. So NOR gate means simply symbol is like this. Two inputs. This is OR gate and this is NOT symbol means this is NOR gate. It is a combination of NOT plus OR. Input A, input B, output Q. Input A, input B, output Q. Okay. Let us see NOR gate. Okay. NOR means this is OR, this is NOT. So OR operation is A plus B. NOT of OR operation is over bar. Q equal to A plus B over bar. Truth table. Input A, input B, output Q. Okay. 0, 1, 0, 1, 0, 0, 1, 1. Okay. 0 plus 0 is 0. Over bar is 1. 1 plus 0 is 1. Over bar is 0. 0 plus 1 is 1. Over bar is 0. 1 plus 1 is 1. Over bar is 0. So in this way you can define logic gates. There are two more gates. Okay. Two more gates.